On April 17th, 2026, a command left a control room at NASA's Jet Propulsion Laboratory in California, aimed at a machine so far away that the signal wouldn't arrive for almost 23 hours. When it finally reached its target, it did something that sent a quiet chill through the space science community. It shut down one of the last working instruments on Voyager 1, humanity's most distant machine, a spacecraft launched in 1977 that is now more than 15.7 billion miles from Earth. This wasn't a malfunction. It wasn't the mission ending. It was a deliberate sacrifice, engineers choosing to kill an instrument themselves rather than risk the entire spacecraft shutting itself down in an emergency it might never recover from. Just weeks earlier, during a routine maneuver, Voyager 1's power had dropped unexpectedly, coming dangerously close to triggering an automatic fault protection system that could have required a risky multi-day recovery, at a distance where every single command takes a full day round trip just to confirm it worked. That sacrifice bought roughly a year of breathing room, time NASA is spending on something engineers have nicknamed the Big Bang, a high-risk, never-before-attempted maneuver that could determine whether these two probes keep talking to us through the 2030s or go permanently silent within the next few years. But here's what almost nobody is talking about loudly enough. Even as it's dying by inches, Voyager is still finding things out there that don't fit our models, things that are actively reshaping what scientists believe about the space between the stars. The universe beyond our solar system is not empty, it is not quiet, and it is not behaving the way anyone expected it to. This is the story of what Voyager found, what it's finding right now in 2026, and why the discoveries coming out of a failing 49-year-old machine may be some of the strangest and most important in the history of space exploration. To understand why this moment matters so much, you have to go back to where it all started in September 1977. Two spacecraft launched within weeks of each other, not because NASA had planned an interstellar mission, but because of a rare alignment of the outer planets that occurs only once every 175 years. That alignment let a spacecraft use the gravity of one planet to slingshot toward the next, visiting Jupiter, Saturn, Uranus, and Neptune in a single grand tour. The window was open, and NASA took it. Both probes were designed with a 5-year lifespan. They were expected to complete their planetary flybys and then drift silently into the dark, their transmitters long dead, their instruments frozen. Nobody seriously planned for what happened next. Voyager 1 finished its planetary work by 1980. Voyager 2 completed its tour in 1989 with a legendary flyby of Neptune, still the only close-up look any spacecraft has ever taken of that distant ice giant. After that, both probes were pointed outward, away from the sun, away from every known planet, into territory nothing human-made had ever touched. And they kept going, and kept transmitting. Year after year, decade after decade, generation after generation of scientists sitting in the same control room at JPL, listening to whispers from machines that, by any reasonable engineering estimate, should have gone silent decades ago. The distances involved are so large they're almost meaningless to a human brain, so it helps to think of them in terms of light instead of miles. Light from the sun reaches Earth in about 8 minutes. A signal from Voyager 1, traveling at that same speed, currently takes nearly 24 hours. On November 15th, 2026, Voyager 1 is projected to cross exactly one light day from Earth, roughly 16.1 billion miles out, becoming the first human-made object in history to reach that boundary. One full day for a signal to arrive. Another full day for any response to make it back. If something goes wrong with Voyager 1 out there, NASA has to wait 48 hours just to find out whether the fix worked. That loneliness, that silence, is difficult to put into words, and yet the probes are still out there, still moving, still measuring, and what they're measuring is changing what scientists thought they understood about the galaxy around us. Start with the power problem, because it's the ticking clock underneath everything else in this story. Both Voyager probes run on radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. Elegant engineering with no moving parts, no solar panels, nothing to burn or refuel. But plutonium-238 has a half-life of about 88 years, and these generators have been running continuously since 1977. As of April 2026, Voyager 1's generators are producing less than half the power they had at launch, declining by roughly 4 watts every year. 4 watts sounds like nothing, but when your entire spacecraft survives on barely enough electricity to power a dim household bulb, 4 watts a year is the difference between continuing the science and going dark for good. To manage that decline, engineers have spent years doing something close to triage on a patient slowly running out of blood, deliberately powering down heaters, cameras, and instruments one at a time to keep the most essential functions alive. Of the 10 identical sets of instruments each Voyager originally carried, 7 have already been shut off. Voyager 2's low-energy charged particles instrument, the LECP, was switched off back in March 2025. Voyager 1's turn came on April 17, 2026, ending an instrument that had run almost without interruption for nearly 49 years, since the day it launched. The LECP measured ions, electrons, and cosmic rays in interstellar space, mapping invisible pressure fronts and shifts in particle density in the region beyond our sun's reach. Losing it is a genuine scientific loss, but the alternative, letting the whole spacecraft trip its emergency fault protection and risk a shutdown engineers might not be able to reverse, was worse. The time bought by that sacrifice is being spent on the Big Bang, NASA's nickname for a complex, never-before-attempted maneuver on a spacecraft this old, this far away, and this close to running out of power for good. The plan involves simultaneously switching off a cluster of power-hungry devices and swapping in lower power alternatives, carefully reorganizing the spacecraft's entire energy budget to free up just enough electricity to potentially keep science instruments transmitting well into the 2030s. If it works, engineers have even hinted the LECP could eventually be switched back on. A small motor inside the instrument has deliberately been left running at low power, just in case. The Big Bang is being tested first on Voyager 2, which has a little more power to spare and sits closer to Earth, making it the lower risk subject. Those tests are scheduled for May and June of 2026. If they succeed, the same maneuver will be attempted on Voyager 1 no earlier than July. Nothing about the outcome is guaranteed. This is a 49-year-old spacecraft running on software that can't be upgraded and hardware that can't be replaced, with a power margin so thin that a single unplanned roll maneuver nearly ended everything back in late February. Every command is a gamble. Every response takes a full day to confirm. And NASA is willing to take that gamble because what Voyager is finding out there is too important to lose. So what exactly is it finding? What does interstellar space actually look like when you measure it directly from inside it with instruments that no other spacecraft in history has ever operated in that environment? The answer, again and again, is that it looks strange. Not strange in a vague, mysterious way, but strange in the very specific sense that the real universe does not match the models scientists built to predict it. Start with the boundary itself. For decades, researchers debated exactly where the heliosphere ends, that enormous bubble of particles and magnetic field generated by our sun, an invisible shell surrounding every planet in the solar system. Early guesses put the edge somewhere near Jupiter's orbit, then farther, then much farther. Voyager kept flying and kept not finding it. Eventually, both spacecraft crossed that boundary, called the heliopause, with Voyager 1 crossing in 2012 and Voyager 2 following in 2018. And what they measured there was not remotely what scientists expected. The plasma right at that boundary was recorded running at temperatures between 30,000 and 50,000 Kelvin, scorching hot, far hotter than the space closer to the sun inside the heliosphere. A thermal wall at the edge of our solar system burning at tens of thousands of degrees, sitting in a region with so few particles that the heat can't actually damage anything, because there's almost nothing there to carry it. But nobody had put a wall that hot into the models beforehand. Both spacecraft measured it independently. It's real, and scientists still don't fully understand why it's there. Then there are the cosmic rays. Inside the heliosphere, the sun's magnetic field acts as a partial shield, deflecting many of the high-energy particles pouring in from across the galaxy. Cosmic rays exist everywhere in interstellar space, but they're noticeably reduced inside our sun's protective bubble. When Voyager 1 crossed the heliopause in 2012, its instruments recorded a dramatic, nearly instantaneous surge in high-energy particles, striking the spacecraft as it left that protection behind. That part was expected. What wasn't fully expected was the sheer intensity of the galactic cosmic ray environment just outside the boundary. Voyager now operates in a region where it's being continuously bombarded by radiation that has traveled millions of light years before striking a small machine built on Earth in the 1970s. The spacecraft was designed to handle radiation, and it's survived nearly 50 years of exposure. But the galactic cosmic ray environment out there is meaningfully more intense than scientists had estimated from indirect measurements taken safely inside the solar bubble. Our sun has been quietly shielding every living thing on this planet for its entire existence, and we only grasped the true scale of that protection once Voyager stepped outside and measured what was waiting on the other side. The plasma itself told a similar story. When Voyager 2 crossed into true interstellar space, scientists found the plasma on the far side of the heliopause running at roughly twice the temperature their models had predicted. The very local interstellar medium, the region just beyond our solar bubble, turned out to be hotter and denser than anyone had calculated. And here's where it gets even stranger. As Voyager 1 has pushed deeper into interstellar space, the plasma density around the spacecraft hasn't stayed constant. It's been climbing year after year, the farther the probe travels from the sun. Between 2013 and 2015 alone, electron density measurements showed a 40-fold increase compared with the baseline recorded just outside the heliopause, 40 times denser, and not gradually, sharply. Voyager is plowing deeper into a region of space that keeps getting more crowded with particles the farther it goes. Scientists have two competing explanations. One holds that interstellar particles slow down as they approach the heliopause, stacking up like rush hour traffic at a bottleneck, with Voyager now driving straight through that jam. The other suggests the interstellar magnetic field, compressing against the edge of our solar bubble, pushes charged particles away from the boundary itself and toward the surrounding medium, thinning out the region right at the edge while building up a denser zone farther out. A zone Voyager may be entering right now. Either way, the steady rise in density that nobody predicted is already forcing a rewrite of what scientists thought they knew about the space between stars. Then there's the sound, or rather, whatever functions as sound in a place no human ear could ever survive. In interstellar space, the ionized gas called plasma can carry pressure waves and oscillations, the same basic physics that lets sound travel through air, just at far lower densities and frequencies. When Voyager 1's plasma wave subsystem, essentially a pair of 30-foot antennas trailing behind the spacecraft, picked up a continuous, persistent hum resonating through the interstellar medium, scientists took immediate notice. Before that, researchers had only detected brief, sharp whistles in the data, short bursts of plasma wave activity triggered whenever a solar eruption sent a shock wave rippling all the way out to Voyager's location. Useful, but brief, like a camera flash. What scientists actually needed was a continuous light, and that's what the hum turned out to be. A steady plasma wave emission resonating around 3 kilohertz, ongoing regardless of solar activity, giving researchers a continuous window into the density of the space around the spacecraft for the first time. Stella Ocker, a researcher at Cornell University involved in identifying the signal, has described it as something close to a single steady note playing constantly, shifting only slightly over time. Not random noise, not an equipment glitch, a genuine, persistent vibration running through the interstellar medium itself, letting scientists measure the density of the space between stars continuously instead of waiting for the sun to cooperate. It's the difference between reading a river by watching for occasional raindrops and finally being able to dip a hand directly into the current. Layered on top of that is what the magnetometer, one of the last instruments still running on Voyager 1, has revealed about the interstellar magnetic field itself. When Voyager 2 crossed the heliopause, it measured that field at around 7 microgauss, roughly 64,000 times weaker than Earth's own magnetic field, but very much still there and stronger than models had predicted. That extra strength turns out to explain something else that puzzled scientists for years. The sun runs through an 11-year cycle of rising and falling activity, and during periods of high activity, with more solar wind pouring outward, researchers expected the heliosphere to inflate, pushing its boundary farther out. During quiet periods, it should pull back in. When Voyager 1 crossed the heliopause in 2012 and Voyager 2 followed in 2018, both during periods of relatively high solar activity, astronomers expected to find a noticeably larger bubble. They didn't. Both spacecraft measured the boundary at almost the same distance. The reason, researchers concluded, is that the interstellar magnetic field is pushing back on our solar system with more force than anyone had accounted for, holding the heliosphere at a roughly constant size no matter what the sun is doing. Our solar system's protective shell is being squeezed from the outside, and the squeeze is stronger than anyone knew until Voyager measured it directly. All of this is coming from two machines that, in the words of former Voyager project manager John Cassani, were built not to fail, but were never expected to last anywhere near this long. Today, in 2026, Voyager 1 has only 2 active science instruments left: the plasma wave subsystem listening for shifts in the density of the interstellar medium, and the magnetometer tracking its magnetic field. Voyager 2 has 3. These handful of surviving instruments, running on less than half their original power, communicating across a gap so vast that commands take a full day just to arrive, are the only tools humanity has ever placed in direct contact with the interstellar medium. Everything else we know about the space between stars comes from indirect measurements, telescopes peering outward from safely inside our solar bubble. Only Voyager is actually out there, actually touching it. And what it's touching turns out to be weirder, hotter, denser, and louder than the models predicted. There's a newer spacecraft now helping fill in the picture, the Interstellar Mapping and Acceleration Probe, or IMAP, launched in 2025. Scientists describe it as Voyager's kind of data taken to a completely new level of resolution, measuring the boundary of the heliosphere in far greater detail than anything that came before it. IMAP orbits a stable point roughly 1 million miles toward the Sun from Earth, building global maps of exactly how the heliosphere interacts with the surrounding interstellar medium. Combined with what Voyager is still sending back, it's producing the most detailed picture ever assembled of the bubble. Our entire solar system lives inside, and every new piece of that picture raises fresh questions. The heliosphere is not the smooth spherical bubble that older textbooks like to draw. It's asymmetric, shaped and pushed by the direction of the interstellar magnetic field pressing against it, stretched on one side and compressed on the other. Our sun is moving through the interstellar medium at roughly 56,000 miles per hour, plowing through a region of space that is actively pushing back against it, and Voyager is riding in the wake of that plow, measuring the churned-up environment left behind as our solar system cuts its path through the galaxy. Whatever happens with the Big Bang maneuver in the months ahead will determine how much more of that territory Voyager gets to map before the silence finally comes. Engineers remain hopeful. The same people who built these spacecraft for a 5-year mission and then watched them keep running for nearly 5 decades are not people who give up easily. If the Big Bang works on Voyager 2 this summer and then on Voyager 1 sometime after July, there's a real chance both probes could keep transmitting usable science data into the 2030s. If it fails, the mission could end within just a few years. Either way, the clock is running and the universe out there, hotter than expected, denser than expected, louder than expected, is not waiting for our engineering to catch up with it. What's particularly striking about where Voyager stands in 2026 is that its most important discoveries are coming from the weakest, most stripped-down version of the mission that has ever existed. At launch, each probe carried 10 sets of instruments, cameras, spectrometers, particle detectors, magnetometers, plasma analyzers, the full toolkit needed to explore a genuinely unknown environment. As the decades passed and the power kept declining, instruments were switched off one by one. The cameras went first, since there was nothing visible left to photograph in the featureless dark of interstellar space. Then the ultraviolet spectrometer. Then others, each shut down a quiet ending for another piece of scientific capability. And yet, the handful of instruments that remain, the ones measuring plasma waves and magnetic fields, the ones directly sampling the texture and behavior of the interstellar medium itself, happen to be exactly the tools needed to answer the questions Voyager is now uniquely positioned to ask. It's almost as if the mission somehow knew which instruments it would need at the very end, kept them alive through years of careful rationing, and is now using them at precisely the right moment to answer questions that didn't even exist back when the probes launched in 1977. The hum running through the interstellar medium, the steadily rising density of the space between stars, the scorching plasma wall sitting right at the edge of our solar system, the uneven, turbulent shape of the heliopause itself. None of these were the discoveries anyone planned for when this mission began. They are the discoveries the universe chose to hand us, delivered by 2 machines that refuse to quietly die on schedule in a place nobody ever designed them to reach. Consider, too, what it means that the heliopause itself turned out not to be uniform at all. When Voyager 1 crossed it in 2012 and Voyager 2 followed 6 years later in 2018, the 2 probes were traveling in entirely different directions, aimed at completely different parts of the sky. Today, they're so far apart from each other that each one is actually farther from its twin than either is from Earth. Yet their 2 boundary crossings looked strikingly different. Voyager 1 recorded dramatic fluctuations in the magnetic field right at the moment of crossing. Voyager 2 didn't see that same magnetic turbulence, but instead detected a thin layer of unusually hot plasma just outside the boundary, a cosmic ray layer that Voyager 1 had missed entirely 6 years earlier. The heliopause isn't a clean, smooth, uniform shell wrapped evenly around our solar system. It's a complicated, turbulent, asymmetric boundary that behaves differently depending on exactly where and when you cross it. Our solar system isn't sitting inside a perfectly symmetrical bubble at all. It's sitting inside a structure being pushed, squeezed, and reshaped by the interstellar environment surrounding it on every side, unevenly, depending on the direction of the interstellar magnetic field, the local density of the surrounding medium, and the motion of our entire solar system as it cuts through the galaxy. Voyager 1 and Voyager 2 have given scientists exactly 2 data points on that boundary, 2 measurements taken at 2 different locations years apart, and even from just those 2 points, the picture that emerged was already far more complex than anything the models had prepared researchers for. It's worth pausing on what that implies about the roughly 2/3 of that boundary that no spacecraft has ever measured at all. Here's what stands out most about this entire situation. We are living through the extraordinary position of having 2 machines, launched before personal computers existed, before the internet existed, before most people watching this video were even born, that are right now, today, in 2026, touching territory that no other human creation has ever reached. They are measuring a place where our best scientific models turned out to be wrong in several significant ways at once. The heliosphere isn't the size researchers expected. Its boundary isn't the temperature anyone predicted. The interstellar magnetic field isn't as weak as scientists once assumed. The density of the medium beyond our solar system keeps rising in ways current theories still struggle to fully explain. And running underneath all of it, steady and persistent, is that hum, a real measurable vibration moving through the plasma between the stars, carrying information about a universe humanity is only just beginning to learn how to read. Every additional day these two probes keep operating is another day of data from a place no currently planned mission will reach again for decades. The next purpose-built interstellar probe, assuming one is ever funded and launched, would take at least 15 years just to reach the distance where Voyager 1 sits today, and considerably longer to push beyond it. For now, Voyager remains the only voice humanity has coming directly from the space between the stars, and that voice keeps saying things that are genuinely reshaping what we understand about where we live and what surrounds our small corner of the galaxy across hundreds of trillions of miles in every direction. The universe beyond our sun is not empty. It is not silent. And after 49 years, 2 dying machines are still out there proving, one faint signal at a time, that it is not remotely what we once thought it was.